Good morning or good afternoon, everyone, depending on where you are. This is the final session for HCI and player experience track. We've had a lot of good papers this year. Now, our new first talk is titled Immersive Gameplay via Improved Natural Language Understanding.
Hi everyone, my name is Berkeley Andrus. I'm with Dragon Labs at BYU, and my paper is called Immersive Gameplay via Improved Natural Language Understanding. The motivation for our paper is we wanted to use speech as a way of interfacing with your NPC teammates in something like a first-person shooter, just like you would talk to a human teammate. The pipeline that we imagined is that the player, who is controlling their own character like normal, is also able to control NPC teammates by speaking to them. The player uses unstructured, totally natural speech as if they were talking to a human. The speech gets converted into text and fed into our natural language understanding system that we've built. The purpose of our system is to translate from the unstructured speech of the user into structured commands that the NPCs know how to execute and act on, creating a smooth, easy interface. In our setup, we defined a command as a verb followed optionally by an object. You can think of these as an action the player wants the NPC to take and a target for that action. These would be things like flee, attack vehicle, exit building, these very basic behaviors that the player might want to trigger in the NPC. These are predefined by the game designer and given to our system. When the user says something like, take out that ship, our system is able to classify that and figure out which predefined command it corresponds to. Our approach is built on the technologies of word and sentence embeddings, so I'll summarize those briefly for those who aren't familiar. A word embedding is a vector that represents the meaning of a word with relation to other words. In this example, the words newspaper and magazine are very similar, so their vectors are geometrically close together. The idea is that the closer two embeddings are, the more similar the words are semantically. Word embeddings are pretty well established, and recently researchers have created sentence embedding tools as well. So instead of embedding a single word, you can embed an entire sentence into one vector. For our experiments, we used two versions of the Infocent sentence embedder, which is just an off-the-shelf, publicly available embedding tool. Using the sentence embeddings, we came up with 4 command extraction methods, 4 different methods for figuring out what a user wants an NPC to do based on what they said. The first one is called simple distance. We start by embedding whatever the user said and the names of each of the predefined commands. I've shown 3 commands here, but in our experiments there were usually somewhere between 20 and 40 different commands to choose from. We then find the distance from the user's statement to each of our commands and use the shortest distance to decide what the NPC should do. For our next method, we hypothesized that there was some portion of the embedding space that corresponded to unstructured natural speech and a different portion that corresponded to structured commands. We hoped that there was some sort of linear translation that would move us from one space to the other, so we could make more meaningful comparisons. To find out what that translation was, we came up with 2 or 3 examples of what we thought a player might say to trigger each of our predefined commands. We then found the distance between each example and its command by subtracting the embeddings. So these blue vectors are the distances. Then we average all the distances to get what we call a translation vector. We add the translation vector to each new user utterance, hopefully shifting it into the space of structured commands before we compare it to the predefined commands. Our third method is called PC distance. For this one, we took the same examples from the translation method and put them in a matrix together, 1 matrix per command. We then found the first principal component and corresponding eigenvector for each matrix. These blue dots are eigenvectors, and we hope that they act as sort of a summary of the example data we've provided. We then take the embedded user utterance and compare it directly to the eigenvectors to figure out which command should be executed. Our final approach was just a nearest neighbor approach. Here, instead of comparing the user's utterance to the names of the predefined commands, we compare it to the corresponding examples. Then, just like before, we take the shortest distance to decide what the NPC should do. We created 4 test sets to test the accuracy of our methods, each with its own commands and user utterances. The first test set we took from NPC dialogue in the World of Warcraft games. The next two we handwrote in our lab with things that we thought people would say while playing Halo. And the final one we consider to be the most valuable test set because it came from real users. We collected it by showing volunteers screenshots from the Call of Duty games and asking them to type out what they would say to get a teammate to accomplish a specific goal. So those user responses became the test utterances for us to classify. Here are the results of using those 4 command extraction methods on our 4 test sets. These numbers are accuracy scores, or the percentage of test cases that were correctly classified. These numbers are a little bit low, but I think that's deceptive for 2 reasons. First, this is before we've tuned some of the other hyperparameters that we talk about in our paper. More importantly, we're not using any sort of game context here, which puts us at a disadvantage. Our model looks just at the user's utterance without any information about how many enemies are nearby, or what situation the player might be in, or anything like that. We think that in a production environment, we would be able to combine game context with the semantic information we've collected to boost these scores to something that would be a little bit more useful. As you can see, PC distance ended up being the most accurate method overall and also on our most valuable test set. We also compared our results to 2 industrial models. The Google Home and Amazon Alexa platforms both have a functionality called intent routing, which is where their voice assistants take a user utterance and figure out which part of their server should respond to it. As you can imagine, this is quite analogous to our command extraction problem that we've put forward. In fact, we were able to reframe all of our test and training data as Google Actions and Alexa skills so we could test their model's accuracy on our data. We found that once we'd tuned the hyperparameters of our model, we were able to far surpass both Google and Amazon on all 4 test sets, which was really exciting. We think this might be because we had so little training data. We were providing 2 or 3 examples for each command when their models were expecting closer to 10. This might mean our model was better at leveraging small amounts of data more effectively. We also think Google and Amazon have probably fine-tuned their models on the kinds of conversations you have with a voice assistant, which is a pretty different domain than conversations you have while playing games. Finally, I just want to share some of our next steps that we hope to take with this research. First, we want to actually incorporate our model into a game. We assume that speech as an interface will lead to more immersive, engaging gameplay, but we want to playtest that to make sure. We're currently looking for collaborators with experience in game design, so if you're interested in using our system, please reach out and we'd love to work together. We also want to try to fine-tune our sentence embedding tools on video game-specific data. Infosent is general purpose, and we are curious to see if we could collect enough data to make a tool that is more accurate on the unique vocabulary associated with sci-fi, fantasy, or combat games. That's our research. Thanks so much for listening, and I think we have a few minutes for questions.
All right, great talk. Questions from anyone? I think there might be some questions in the chat.
I have a question for Berkeley.
Go for it.
Okay, how do you do it seems that the table that you showed about accuracies, it all depends on how many possible destinations there are for the classification, right?
Yeah.
And how many were there?
Yeah, a good question. So I think we include the exact numbers in our paper, but there were the smallest test set had 12 options, and the largest one had around 30, I think.
Uh-huh. And if a follow-up, if you don't mind.
Yeah.
How do you did each set also have a none of the above option, and was that a particularly difficult thing to handle?
We did not. Yeah, in hindsight, I wish we had addressed that from the beginning, because that would be a big consideration if we wanted to actually use this in a system. But in these experiments, we didn't include a none of the above option.
So does that mean every utterance in your test would have correctly been classified as one of the options that you had?
Yeah. So in our test set, there was always a right answer. but that means that if you actually used this in a game and the player mumbled under their breath or said something that wasn't supposed to be a command, we would try to interpret that as a command. So that's definitely something we would need to address before we applied this.
Thank you.
Yeah, thanks.
Looks like the author for the first paper is not here, so we might have a little more time for the QAs for the remaining 3 papers. Any other questions?
It looks like someone in the chat gave some examples of games that use similar techniques. I haven't heard of those, so I'm going to have to look at those and see what they're doing.
Yeah, I think there are quite a few comments in the chat, but I don't see a question. Or if there's no other question, oh, let me see. I've never tried it. There's another comment in the chat. I do have one question. So we're doing some of similar work, not in the context of games, but trying to understand how do you improve learnability for voice user interface overall. So I wonder in your particular case, right, when you have a very clearly defined task, things or domain, the games you're playing, I wonder what you think are the obstacles for the players to know what to say. They might have, so in voice user interface, I think there are sort of 2 concepts in terms of voice commands, right? One is the utterance, which is exactly what words to say to trigger certain actions. And the second one is, I think it's called intent, which is what is that you want to do. So in the context of your game, so if they're players, they're familiar with the game, I imagine most people will know what their the actions they want to perform is, but they may not know what exactly to say. I wonder how, as a game, especially from the HCI point of view, how can you give enough scaffolding for the player to say, this is what the commands are, and this is the right way to say it, especially when they also have all the other things going on in the game?
Yeah, that's a great question. Learnability was a big motivation for all of this work. Because of course, if you gave the player 20 commands to memorize, then the system would work really well, but we didn't want to do that. I feel like what we've experienced with voice interfaces over the last 10 years with Siri and Alexa and all of that is that users get better at it over time, but it can be frustrating at the beginning when you don't quite know what words to use and how to structure your sentences, just like you've said. I think our goal here was that if we could just loosen up the restrictions a little bit and make it a little bit more accessible, then even if the players aren't having 100% success at the beginning, they're having enough that they're motivated to keep engaging with it and learn over time what works and what doesn't. Yeah, as we play test it, though, we might find that we need a little bit more onboarding than that, but we're hopeful that this is a little bit more flexible than what exists already, and that will give players enough of a starting point.
Yeah, I think this is a place, maybe that concept of flow, sort of like if you can incorporate the lessons that we know from good game design into voice user interface onboarding and learnability. I think that could be something interesting there.
Yeah.
But fascinating research.
Thank you.
Is there anything else? Let me see. I think there's one more message.
Yeah, someone asked about
why do you think the PC method gives the best results overall?
Yeah, that's a good question. I was surprised by that. I thought that the translation method would do the best. Yeah, I don't really have a good answer for that. I guess it just was able to do the best job of summarizing the entire output class with the least amount of data because we were using so little training data.
All right, if there are no more questions, let's thank our speaker. And the next paper that will be presented here is titled Reading Between the Lines Towards an Algorithm Exploiting In-Game Behaviors to Learn Preference in Game for Systems. Is this a live presentation or is this a video?
No, it's a video. I'm playing it right now. Hi everyone, I'm Enrica Loria, a PhD student from the University of Trento, Italy, and the FBK Research Center, also based in Trento. And today I'll present you our study on players' behaviors to model in-game preferences on behalf of my colleague Anna Paola Marconi. Let me start by presenting our research. Our focus is on the analysis of players' behaviors and experience to understand how users interact in the game. The goal is not only to reach a greater knowledge on players, but also to provide methods to improve the gaming experience. Our application domain range between both entertainment games and gamification. In the present study, we analyze data from a gameful system. Player modeling and the generation of tailored content is essential as perception is highly subjective. What immerse and engage some users could also completely discourage or bother others. This is particularly relevant in gamified environments, as gamification aims at making everyday or tedious actions enjoyable and gameful. Players' retention is likely to be improved by adapting the experience to the player's preferences. Users should play because they enjoy the experience and because they have fun. The goal of player modeling or profiling is to better understand players, but also to provide them content that is closer to their tastes. For instance, they might prefer solo play rather than playing in teams, or they might want to be challenged by the game with difficult tasks. As important is to consider how, while some players view customization as part of the fun game experience, and thus they explicitly manifest their preferences, another portion of users is indifferent, if not annoyed, by the possibility of making choices. Yet, also those users expect the game to modify itself to adapt to their tastes and skills. Therefore, a question arises. How can we learn player preferences without relying on players explicitly expressing them? Telemetry data can be used towards this, as it is easy to implement logging mechanism to transparently store players' activity. This data, then, can be treated to measure in-game behaviors, which can be analyzed and monitored over time. So the question becomes, how can we exploit this telemetry data to learn their preferences? Which can be translated to, how can we read between their in-game behaviors to learn more about them? We saw a similarity between learning from experience and using in-game behaviors throughout the gameplay to learn players' preferences. Therefore, we conducted a feasibility study, exploring the idea of using players' activity level as feedback for the generated game elements in an algorithm inspired by the reinforcement learning paradigm. Although currently the algorithm works with offline data, and thus it's not a real reinforcement learning algorithm, the aim is to set the ground for introducing it as a content generator integrated in the system. Specifically, we used a variant of the multi-armed bandit problem, namely the gradient descent. Here, rather than finding the optimal choice, the goal is to estimate a preference score for every action, or bandit. In our formulation, the bandits are the available types of the game element to personalize. The data analyzed has been collected from an open-world persuasive gamified system, promoting ecological mobility habits. The game is active in 2 Italian cities, and citizens can voluntarily participate to sponsored gamification campaigns, lasting for about 6 months. Players can track their movement within the city by specifying the transportation means used. In this study, we focused on game challenges, as this is the content that can be customized. Challenges must be completed within a week, and if won, awards players additional points. Challenges can vary in the target requested, which is in the form and number of kilometers or trips to perform. Therefore, challenges can be either computed on walk kilometers, bike kilometers, train trips, bus trips, or more in general, on game points. As players gain experience and advance in the game, they also acquire the possibility to customize their challenges. And thus they can provide a choice between 2 or 3 options. It is important also to note that customizing a challenge is not compulsory, and thus from our population of players we had to exclude players that never made choices. This led us with a sample of 94 players. This restriction was needed as players' explicit choices were used as ground truth to evaluate the algorithm's performance. Both the algorithm and the analysis of in-game explicit choices produce numerical values associated to the challenges types that we can see in the picture. As those numbers are not comparable because they were computed through different methods, we compared the sorting of the options. In the figure we can see an example of how the ground truth sorting and the algorithm sorting are compared. Specifically, we have that the order of the first 3 options are mixed up, while the last 2 challenges types are ordered in the same way. To evaluate the algorithm's performance, we used as error measure the normalized root mean squared error, which gives a relative percentage of the error obtained. To assess the similarity between the 2 non-zero vectors, we used cosine similarity and R-square, which measures the proportional variation in the dependent variable that can be attributed to the independent variable. As the table shows, the evaluation of our algorithm had very variable outcomes. For instance, the error spans between 0 and 0.8, while the similarity computed to the R-square matrix ranges between -3 and 1. We found that for 51% of the players, their predictions were very accurate, while for the remaining users, the algorithm worked purely. Thus, we investigated further the causes of such variability. We divided the initial set of 94 players in the ones achieving good performance and in the ones for which the algorithm failed in learning their preferences, and tested 4 hypotheses through the Mann-Whitney test. First, as players could have been exposed to a smaller set of challenges types, we tested whether this number affected the algorithm's accuracy. Although we found that a smaller number of options correlated to better performance, the number of choices per player in the 2 groups were still well distributed. Thus, this was not a factor. Then, we tested the hypothesis by which having more algorithm iterations produced better results. However, that was not the case. In the third hypothesis, we investigated if the strength of preferences players manifested in the explicit choices impacted the performance. Towards this, we measured the relative standard deviation of the preference scores from players' in-game choices, used as ground truth. The algorithm succeeded in learning preferences for players that manifested stronger preferences. We also researched the causes of such heterogeneity in players' identity, here represented by the exact user types. However, player types cannot be used to identify players for which the algorithm will perform well. To summarize, we conducted a feasibility study showing that implicit preferences can be extracted by feeding players' participation behaviors to a reinforcement learning-like algorithm. However, we observed very variable results in terms of accuracy, which is affected by the strength of players' preferences, measured in their explicit choices. Other factors, such as the number of iterations of the algorithm or players' types, did not affect the algorithm's performance. In the future, we plan to upgrade the algorithm from an offline to an online algorithm. Having assessed the feasibility of using participation data to inform players' preferences, we can go back to the initial inspiration, a reinforcement learning algorithm. Therefore, The goal is to learn players' preferences online and to deploy the best choice for every player. This would result in a one-line modification in the algorithm. Following interesting investigation, we'll be studying the time needed for the algorithm to converge and its ability to adapt to preferences shifting. Finally, an interesting perspective could be comparing the quality of the results also in a more complex environment to understand whether the increased complexity facilitates or hinders the applicability of the approach. To summarize our outcomes in 2 sentences, we observed how players' participation behaviors can be used to learn their preferences regarding a specific game element. Nevertheless, for the algorithm to provide accurate results, players must show stronger preferences among the options available. That concludes the presentation. If you have questions or comments, please feel free to contact me, either on Twitter or email. Thank you for your time.
Thank you for a very nice presentation. I should also mention this is one of the papers that was awarded the exceptional paper in this track. Congratulations.
Thank you.
So now we have a couple of questions on, one question on the chat.
Yeah, okay. So the question is that probably external causes such as weather or specific needs may also affect the choices of players, so the explicit choices. And yeah, that definitely is one of the limitations of this approach, that but in general is one of the limitations of all the analysis that we can run around this application, because external causes are very strong. So one thing that may attenuate this limit is the fact that the game runs for about 6 months. So it's quite a long period of time. So we expect that preferences can emerge, so during that time, yeah. Thank you.
I have a question as well, if we have time. So,
oh, we have plenty of time.
All right, cool. So yeah, it was a really interesting talk, so thanks for that. I still need to read the paper, so apologies if this question is a bit naive. But I'm just wondering, do you think that player sort of behaviors and preferences and all that would perhaps change over time, sort of like beyond what you initially measured?
Yeah, that's actually a very interesting question. And as I briefly mentioned, that's definitely something that we want to explore. And it's sort of what got us started, because with an approach like that, and not using player types approaches with questionnaires and stuff, you can accommodate this shift potentially. So yeah, that's definitely something that we're working on.
Thanks.
Any other questions? All right, I have a quick one. So Enrica, can you tell us maybe just a little more about why, sort of the motivation of why did you decide to use the multi-arm band-aid as the algorithm?
Mm-hmm. Okay. Yeah, so the idea there was to kind of sort the option, and the idea of using reinforcement learning came from learning from experience, right? So the idea is you give players challenges, because if they do not choose challenges, they are automatically assigned. And you see how they behave. And if they interact with the game more, you expect that they are enjoying those game elements more. And so the choice fell on the gradient descent, because we needed the sorting, basically.
Yeah, thank you. I think we just published, we also have a paper earlier about using a maybe, but in a combined online and then offline and then online learning. I'd love to chat with you more afterwards.
Oh yeah, I would love that. Sure.
All right, let's thank our speaker. And the final talk in this session is intensifying stress perception using visual effects in VR games. No rush, we have time. And also, I just want to thank David and everyone else who has been chairing sessions. It's hard to know because it's a thing that you don't see, but I've never been so overwhelmed with all these panels, these different things, and looking at these different platforms.
Hello, and thank you for having me at the FDG conference in 2020. My name is Sebastian Mishtal. I'm with the Interactive Reality Experiences Group at the University of Applied Sciences and Arts in Hanover, and I present you our paper, Intensifying Stress Perception Using Visual Effects in VR Games. Our paper is motivated by the problem that common output devices, such as game controllers, displays, head-mounted displays, or headphones, are limited to tactile, visual, and auditory feedback. So many sensory experiences are unavailable in video games when you're using these common output devices. In another work, where we investigated character-centered video games, we found out that many game designers use visual effects to substitute these unavailable experiences and senses to perceive, for example, fear, discomfort, or stress. You can see an example in the picture which shows a scene of the game Amnesia: The Dark Descent, where the game designers used a blur effect and a color grading effect to at least partly substitute the feeling of fear, discomfort, or stress. But most visual effects have not yet been investigated with regard to the influence on the human perception. In our work, we want to investigate the substitution of a sensation, in our specific case, the sensation of stress, with visual effects that represent related symptoms of stress. For example, acceleration of heart action, shaking, lightheadedness, or loss of peripheral vision. And with our work, we want to contribute to game research and show how players can experience certain perceptions of the player character that were previously unavailable, at least partly through the visual modality. Here you can see the visual effects we used. We used vignetting, which results in a darkened peripheral view to substitute loss of peripheral vision. We used image noise, which results in a grain effect to substitute acceleration of heart action in combination with the pulsating vignetting. We used chromatic aberration and color grading, which results in color distortions and highlights of certain colors, in this case red, to substitute shaking. We used depth of field, which results in a blur effect to substitute lightheadedness. We tested our visual effects in combination in a game experience, which is typical to a stressful situation in action games. The player has to monitor the events which are happening outside and can experience the visual effects. Inside, the player can also interact with objects. In our study, we wanted to investigate whether the visual effects we use for related symptoms of stress can contribute to subjectively perceive more stress. And we also wanted to investigate whether the visual effects negatively influence relevant VR experiences such as presence and simulator sickness. To investigate stress, we asked our participants to what extent the visual experience in the game scene contributed to increase their perceived stress on a 7-point Likert scale. To investigate simulator sickness, we let participants respond to the simulator sickness questionnaire on a 4-point Likert scale, and to investigate presence, we let participants respond to the iGroup presence questionnaire with all 4 items: a sense of being there, spatial presence, involvement, and experienced realism. Our study was conducted with the Oculus Quest head-mounted display and within subject design. So each participant had to play the game experience twice, once with the visual effects and once without the visual effects. After the introduction, the participants played the Oculus Quest test scene to learn the use of the HMD and the controllers. Then they had their first game experience. After that, they responded to the stress, IPQ, and SSQ questionnaires, and then they had their second game experience with or without the visual stress effects, depending on their first game experience. And in the end, they had to respond to the stress, IPQ, and SSQ questionnaires again and gave qualitative feedback and demographics. We recruited our participants via convenience sampling at our university, and they were not remunerated. 6 people participated with an average age of 24.17 years, and all participants stated that they had a quite high game expertise. Here are the results. Regarding the first research question, participants subjectively perceived slightly more stress when exposed to visual effects compared to experiencing the VR scene with no additional visual effects. Regarding the second research question, presence and simulated sickness were reported with no significant differences between both conditions. We conclude that visual effects can contribute to subjectively perceive more stress. These results are interesting for first test, but they have to be interpreted with caution because stress scores are relatively low on both conditions and the sample size is quite small, and we had a very short play time. We also conclude that visual effects do not negatively influence perceived presence and simulated sickness. Simulated sickness was relatively low in both conditions, between none and slight, and presence was relatively high in both conditions, especially sense of being there and spatial presence. Participants probably felt situated in this scenario and could possibly sympathize with others in such a situation. We also suggest that the VR technology might also explain high presence scores. For future work, we want to investigate the effects individually and not in combination like in this study. We also want to measure the players' electrodermal activity to get more precise results regarding the stress level of the participants. And we want more comprehensive testing. Clearly a bigger sample size, more interactive game elements, and longer play time. Here are the references used for these slides. Thank you very much.
Thank you. Questions?
I have a question once again.
Please.
Yeah, so it was quite interesting. Just so it's mainly for like a clarification sort of question. So when you use the effects of pulsating and everything, is that sort of like automated in the sense that if I'm looking at, no matter what I'm looking at, it's always the same, or does it change? Does it adapt basically to what I'm looking at? This is my question.
Yeah, it's adapted to what you were looking at, and especially to the interaction, the grenades and the projectiles coming from the side and the sound and so on. Yes.
Okay, yeah, that's pretty cool. I think also, like, I wonder, do you think that could contribute? Because in a way, it's sort of like sensory immersion, right? So could that contribute to like an increased flow state, perhaps?
Maybe. Good
Yeah.
question. We should probably test that, but I can say.
Yeah. It was quite interesting. So thanks.
Other questions?
I can ask a question. It's really promising. Can you hear me?
Yeah.
Yes.
It's very promising that you don't experience adverse effects from motion sickness, etc., with the extra visual effects. I wonder whether this can be like whether there's a limit. So you chose the visual effects up to a degree, and that caused an effect. What I'm trying to say is, if you wanted to turn the impact, the emotional impact or the effective impact up to 11, would that also cause an issue? Motion sickness, etc.
Yeah, very interesting. Yeah, we should probably test this too. But very good point. Yeah, thank you. Very good point. Yeah, I'll write that down for me. That's very good.
Hi, I have more a suggestion maybe than a question, if you don't mind.
Yeah.
Okay, can you hear me?
Yeah, sure.
All right. So first of all, thank you for that. It was a very clear presentation, and it's a really interesting study. I've worked in VR, so using the kind of tricks for that sensory deception is really interesting and cool. So well done on that. My main slight criticism, I could say, was on the actual investigation study, and specifically your sample size. One, I think 6 people is a very small sample size, to be honest. So I really wish it would be on a bigger sample of people, so we could have more significant results. And another thing is that you mentioned that the sample population were gamers, basically. And what I noticed is that there's a big gap between gamers and not gamers when it comes to how they can handle VR, right? Gamers are used to 3D worlds, they're used to VR, so it's much easier for them to handle, but non-gamers struggle a lot more, they get dizzier, more fatigue, sickness. So with regards to your results, it was interesting that your results state that it increased the engagement, but it didn't make them more nauseous or whatever. But I'm curious to see if that same effect would hold for non-gamers. So I think if you had to repeat the study with a larger population and more average Joes rather than gamers, I think it would be really interesting to see those results. So if that would be possible, I'd definitely be interested to see that.
Yeah, that's right. I will have to say that we consider this investigation more like a first test. So to investigate if these visual effects in any way
If they trigger the users in any
some
way, you mean?
problems like with presence or simulated sickness. But you are right when you say that the sample size of 6 participants is very low, and this is what we mentioned in our paper too. And this is definitely what we have to do in the next study to get a bigger sample size. But the other point. It's clear to me too that you think that maybe non-gamers would respond in another way to the stress symptoms, but gamers are clearly our target group. So we wanted to test these effects with gamers. So this is why we did this. Yeah.
Okay, in that regard, if it's specifically for gamers, then yes, I agree, it makes sense. Thank you.
Yeah, and biofeedback would definitely help too. As I said before, it's more like a first test, and to investigate whether these effects cause some problems with the participants and the players. And in the next step, we have to do a more sophisticated measuring with regard to the stress levels. So definitely using biofeedback too.
All right. So I just get a note that we want to aim to end 10 minutes before so that people can take a short break. So I think Rafa did just post this question. So maybe I'll suggest take this to the, I'm blanking out today. To all the other social media platforms we have and can, oh, okay. All right, Discord, thank you. Sorry, just have a brain damage recovered from yesterday was the Kai submission conference. So I'm kind of running on my 6th coffee today. Well, really nice talk, everyone. Thank you so much. It's been a great track. Yeah, I think enjoy the rest of your conference and see you around.